All right, guys, this video is a kind of an overview of vectors. And at the very end, we will connect this and basically talk about vectored value functions and how that kind of relates to parametric equations. Very similar. So a lot of this won't necessarily be tested, but we just want to make sure that we're all on the same page with vectors. So it says in geometry and physics, there are many concepts be quantified with a single number. These are called numerical quantities. And they're represented by a scalar, normal. All right, so however, there are some concepts that require a different representation, mainly because there needs to express both quantity and magnitude, or direction. I don't say magnitude and direction, I don't know if I said quantity. Magnitude and direction. And I don't know how I forgot that. Think about the Despicable Me movie, that vector, he says it over and over. My kids watch it over and over, so I don't know how I messed it up. But vectors represent both quantities that have magnitude and direction. So the magnitude, like how long the vector is, and then the direction, which way it's facing. So concepts that are expressed by a single number: temperature, mass, time, length, area, volume. Concepts that are expressed by a vector: force, velocity, and acceleration. And those last two are familiar with calculus. To represent a vector, we use a directed line segment as shown below. The directed line segment PQ has initial point at P, terminal point at Q, and we note the length, the magnitude, by those two bars separated by PQ. That's the magnitude. Two directed line segments have the same length and same direction are called equivalent. For example, all these vectors are equivalent. We call each vector in a plane, we can write it by a lowercase letter instead of the terminal point and initial point. So boldface, lowercase letters are how we represent vectors often. So equivalent vectors, again, not necessarily a tested topic, we're just trying to get an idea of what vectors are. Let U be a directed line segment from 0 to 5.5, and let V be represented by the directed line segment from -1, 3 to 4, 5. Show that those are equivalent vectors, so they have the same magnitude and direction. Same magnitude, so the same length, which we'll talk about in a second, and the same direction, so the same slope. So for U, I'm going to find the slope by doing y2 minus y1 over x2 minus x1, and I get 2/5. The magnitude, which I could represent by the two lines of U, the magnitude of that is just the distance from those 2 points. So the distance formula, 2 minus 0 squared, so y2 minus y1, x2 minus x1, doesn't really matter, plus 5 minus 0 squared, and that would be what? 2 squared, which is 4, 5 squared, which is 25, so the square root of 29. So that's the magnitude of U. All right, so let's see, the V, I've got to show that they're equivalent, so I've got to show it has the same slope. Slope will be y2 minus y1 over x minus x2, so that'd be 2/5, so they're the same. And then the magnitude of V would be equal to the distance formula of 5 minus 3, the difference in the y's squared, plus the difference in the x's squared. Running out of room. And that's also equal to the square root of 29. So, couple things there. If I wanted to draw them, I don't really want to draw them. But starting at 0, 0 to 5, 2 would look kind of like that. So the rise and the run, I could also make this 2 and 5, do the distance formula that way. Anyways, so those vectors are equivalent because they have the same magnitude and the same direction. Okay, line segments whose initial point is the origin, whose terminal points are at V1, V2, given by the component form, which is what we're going to see a lot. like the V will have like it'll have these little like, I don't know what those are called, just pointy brackets. It's going to be component form. So V1 is the terminal X point, and then V2 be the terminal Y point. And when you graph a parametric equation, you're graphing all the terminal points. So that's something that I'll say again later, but I'll make sure I say it now. So just vector basics. Magnitude is the length. Direction, vectors can be represented by directed line segments. We know that. Magnitude. There's a horizontal component, which will be the X part. That's the horizontal component. The Y component would be the Y part. And sure, that's it. All right, notation. The most common form we'll use is this component form. And you'll see this a lot. So if I see these vectors where the X component is given by a function and the Y component is given by a function, it's written like that. Okay, rarely it'll be given to you like this with unit vector. Actually, don't think I've ever seen one like that, but it could see like that. So if you see the I and the J, that's just a vector value function, which we're going to basically treat the same as parametric form. It's got